This is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. Today I am going to discuss about metal oxide semiconductor field effect transistor, that is termed as MOSFET. So while coming to the contents here, I am going to discuss what is meant by MOSFET and what are the basic differences between the BJT and MOSFET, and what are the classifications of MOSFET, and what are the constructional details of different types of MOSFET, and operation of different types of MOSFET, and voltage current characteristics of MOSFETs. And next, the application of the MOSFET, that is how we can use it as switch. So here is the MOSFET. So MOSFET is nothing but, I have mentioned, it is called as metal oxide semiconductor field effect transistor. So here MOSFET consists of three terminals. Those are gate, drain, as well as source terminals. So if you take any type of MOSFET, that may be junction MOSFET or enhancement MOSFET or depletion MOSFET, it consists of three terminals. Those are gate, drain, and source terminals. Gate, drain, and source terminals of the MOSFET. So this is the MOSFET chip available in the form of IC here. So this is the one of the type of the MOSFET here. So here MOSFET is nothing but the electronic device. It is the voltage control device, we can say. Why? Because the current conduction in the case of MOSFET is due to the applied voltages, not due to the input currents in the device. So that's why it is called as voltage control device. So these particular MOSFET we can use for the switching application as well as amplification application. Okay, MOSFET we can utilize it for switching as well as amplification purpose. So before going to the construction and operation of the MOSFET, first of all we have to know what is the difference between the bipolar junction transistor as well as MOSFET here. So in the case of BJT, and if we take the MOSFET here, so in the case of BJT we are having three terminals here. Those are emitter, base, and collector terminals. So in the case of MOSFET, also having three terminals. Those are gate, drain, and source terminals. So if we compare with the input impedance, so input impedance of the BJT is low compared to the input impedance of the MOSFET. And in middle, JFET is having medium input impedance, but MOSFET is having highest input impedance. And BJT we can use for switch as well as amplifier, and also MOSFET also we can use it for switching as well as amplification. Okay, and BJT is having negative temperature coefficient, and FET is having positive temperature coefficient. And one more thing here, it is BJT is current controlled device. And MOSFET is voltage controlled device. So why we are calling it as BJT is the current control device and MOSFET is voltage control device means, if we take any BJT here, suppose it is having the terminals collector, emitter and base terminals of the BJT here. So in this case, if you find the collector current that is equal to beta into IB, that is nothing but current amplification factor into input current. IB is the input current or base current. And similarly, if we see in the case of MOSFET, we will be having gate, drain and source terminals. So in this case, the drain current ID is depending upon the VGS voltage as well as VDS voltage. That is nothing but the voltage applied between the gate and source terminals as well as voltage applied between the drain and source terminals. Because of the two voltages, there is a variation in the drain current, that is output current in the case of MOSFET. So that's why it is called as voltage control device. The current conduction is due to the applied voltage, and here BJT is the current control device. Why? Because the current conduction is due to the input current or base current. So these are the major basic differences between the MOSFET as well as BJT. The thing is, while coming to the applications of both the BJT and MOSFET, both are utilizing for same switching as well as amplification. But here, the remaining parameters are varying here. Input impedance and the operating levels are different. So depends upon our application requirement, we can choose any device here, either BJT or MOSFET. So next, while coming to the classification of MOSFET. So before coming to the classification of MOSFET, in the case of FET, field effect transistor, we are having two types. That is JFET, that is junction field effect transistor, as well as MOSFET, metal oxide semiconductor field effect transistor. So these JFETs are available in depletion mode only, but MOSFETs are available in both the depletion mode as well as enhancement mode. And again, in the depletion mode, we are having the N-channel MOSFET and P-channel MOSFET. And similarly, in the case of enhancement MOSFET also, we are having N-channel enhancement MOSFET as well as P-channel enhancement MOSFET. So these are the different types of the MOSFETs are available. So in this, I'm going for the N-channel depletion mode MOSFET here. So before going to that, what is the basic difference between the depletion mode MOSFET as well as enhancement mode MOSFET? That is, in the case of depletion mode MOSFET, the physical channel is present between the source and drain terminals of the device. But in the case of enhancement model, there is no channel, no physical channel exists between the source and drain terminals. So in this case also channel can be formed, but when you are providing the biasing voltages to the enhancement MOSFET only, it can create the channel and it can provide the current. But in the case of depletion mode, in the construction itself, we will provide the channel. So that is the basic difference between the depletion mode MOSFET as well as enhancement mode MOSFET. So while coming to the depletion mode N-channel MOSFET, to construct that, I am considering the P substrate, a piece of P type of semiconductor material, that is nothing but P substrate. So for this substrate, we are having the terminal, we can call it as SB or S. Okay, on this heavily doped P type of substrate or semiconductor material, we are diffusing two pieces of N type of semiconductor materials. Those are here. This is N and this is also N. And we have already known, in the case of N type of semiconductor material, majority carriers are electrons and the minority carriers are holes. And similarly, in the case of p-type of semiconductor material, the majority carriers are holes and the minority carriers are electrons. So here we are considering both the p-type of semiconductor material as well as n-type of semiconductor material. So after diffusing the two pieces of n-type of semiconductor into the p-type substrate, we are forming the metal layer. We are forming the metal layer on that two pieces of n-type of semiconductor materials. So from this we will get the terminal source and drain terminals. And in between these two type of semiconductor materials, we are adding the layer of silicon dioxide. This is the silicon dioxide layer. So upon this silicon dioxide layer, again we are forming the metal layer. So this terminal we can call it as gate terminal. So actually we said that MOSFET is having three terminals, source, gate and drain terminals, but along with this we can also have substrate terminals. But for simplicity, always we will tie both the substrate as well as source terminals and we are make it as single source terminal only. We can also take in that way. So this silicon dioxide layer acts like an insulator between the gate as well as the channel which is present between the source and drain terminals. So this is the N channel. Why? Because it is forming between two N type of semiconductor materials. So once the channel is N type, so that's why it is named as N channel depletion mode MOSFET. Okay, this silicon dioxide layer acts like an insulator between this gate terminal as well as channel here. Because of that reason, we can also call it as MOSFET as IGFET. That is nothing but insulated gate field effect transistor. Okay, MOSFET is also called as insulated gate field effect transistor because of adding the silicon dioxide layer between the gate and channel. Suppose if we take the junction field effect transistor, we don't have any silicon dioxide layer. So that is the JFET. If the silicon dioxide layer is not present, means this structure belongs to the JFET. But here we are making the MOSFET, so that's why we have to add the silicon dioxide layer. Okay, this is the construction of the N-channel MOSFET here. So while coming to the operation of N-channel depletion MOSFET, so it will operate with the different voltages here. That is nothing but when VGS equal to 0, what is the operation of the MOSFET we are going to see. And when you are applying the negative voltage between the gate and source terminals, how much current we are expecting from the device. And when we are providing the positive voltage between the gate and source terminals, what is the drain current or output current we are going to get. So these are the three cases of operation of the MOSFET. So in order to see the effect of these voltages, I am considering the N-channel depletion MOSFET, whatever we designed in the previous slide, same one I have considered here. So in this case, I'm not providing any voltage between the gate and source, that is VGS equal to 0. We are not providing any voltage between the VGS. But I am providing the voltage between the drain and source terminals. That is VDS voltage. That is nothing but we are taking the case 1. In that case, VGS is equal to 0 and VDS is equal to positive voltage we are applying. So in this case, what will happen? Here we are not providing any voltage to the gate, so there is no flow of current through the gate terminal here. But we are providing the voltage between the drain and source terminals. So here the positive terminal of the battery is connected to the drain terminal and the negative terminal of the battery is connected to the source terminal here. So here drain terminal is the N-type of semiconductor material. I have already mentioned in the case of N-type of semiconductor material, majority carriers are electrons. So that electrons are trying to move towards the positive terminal of the battery here. So the electron movement is from drain to source here. Why drain to source means source is connecting to the negative terminal and source is also N-type of material. So both are repelling here. Okay, so these electrons are flowing in this direction. Okay, but they are away towards the negative terminal in the case of source. So once the electron flow is in this direction means, so the current direction in the device is from so ID current will be flowing in the device. So the current direction is opposite to the electron direction. So the current direction is in this way. So we will get in this situation IDSS, that is nothing but constant drain current we will get. If we increase the drain to source voltage also, we will get the constant current, that is IDSS in this case when your VGS equal to 0 and VDS is positive. And similarly, if you take the case 2, that is VGS is equal to negative voltage and VDS is equal to positive voltage. It is nothing but between gate and source, we are providing the negative voltage, VGS voltage, and between drain and source, we are providing the positive voltage, that is VDS. So in this case, what will happen means, see here P-type substrate is having majority carriers are holes, but the minority carriers are electrons. Okay, and these majority charge carriers are now attracting towards the gate terminal. Why? Because gate is connected to the negative terminal. So here the holes are moving in this direction and already electrons are present in the N-type of channel. So because of this movement of majority charge carriers from the P-type of substrate to N channel, the recombination process will start in the channel. So because of that recombination process, the total current ID, previously how much it was flowing in the device, will decrease here. So the ID current will decrease here. So how much gate to source voltage if you are increasing, that many number of charge carriers are combining with the charge carriers which are present in the N channel. So because of that recombination process, the drain current which is flowing through the drain to source terminals is decreases here. So in this particular condition, your current is decreasing here. And similarly, if you take the next case, that is the third case, in this case we are providing between the gate and source as the positive voltage and between drain and source also positive voltage. That is nothing but minus plus, this is VGS voltage, and here it is also a positive voltage, minus plus VDS voltage. So ID current is flowing here because of applying the VDS voltage. But when you are providing the VGS as positive here, in that case, because of this positive polarity of the battery, the minority charge carriers which are present in the P-type of substrate, those are electrons, are trying to move towards the channel. So in the channel, we are already having the more number of electrons. Why? Because it is N-type of channel. So it is having N-type of charge carriers. For that again, we are adding more number of electrons here, more number of charge carriers in the channel because of providing the positive voltage here. Because of this positive voltage only, these negative charge carriers are attracting towards the channel here. So the number of charge carriers are increasing in the channel. So once the number of charge carriers are increasing the channel means the drain current will be increases. Once the electron flow is increasing in the device means automatically the current conduction will be also increases. So we can summarize here, when VGS equal to 0, VDS is equal to positive voltage, we will get the drain current as the constant saturation current IDSS. And when VGS equal to negative voltage and VDS is equal to positive voltage, in this case the drain current is decreasing due to the negative voltage for the gate. And when VGS equal to positive voltage and also VDS is a positive voltage, in that case the drain current is increasing here. So we can say the depletion type of MOSFET will operate in both the depletion mode as well as in the enhancement mode. Depletion mode means decreasing current and enhancement mode means increasing current. So when VGS is negative means this particular MOSFET will operate in the depletion region. In that region the current will decrease here. So when the gate to source voltage is positive, it will operate in the enhancement mode. In that case the drain current will be increases. So this particular thing we can observe in the voltage current characteristics of the MOSFET. So in the voltage current characteristics of MOSFET, we are having two types of characteristics. Those are drain characteristics as well as transfer characteristics. That is nothing but drain characteristics means we will take IDS versus VDS for different values of VGS. So this will give the drain characteristics. And similarly, if we take the transfer characteristics, it will give the IDS versus VGS. This will give the transfer characteristics. So first we will see the drain characteristics of the MOSFET, that is between the VGS versus ID here. Okay, so in this case, when VGS voltage is 0, in that case you will get the current as ID, this is constant current. And when your VGS voltage is negative here, -1, -2 and -3 volts like that, the drain current is decreasing here. So how much if you are increasing the negative voltage, that much drain current is decreasing here. Okay, and if VGS is equal to more negative value and even though you are not providing the VDS voltage means, at that case we will get the current ID is also 0. In that case we can say the MOSFET is in off state. Both voltages are zeros. VGS is equal to 0 as well as VDS is also 0 means there is no current will be flowing in the device, so that we can say the device is in cut-off state or non-operation state. And similarly, if we increase the VGS voltage in the positive direction, that is nothing but positive values, the current ID will be increasing. So that's why this region we can call it as the depletion mode region, and this region we can call it as the enhancement mode region. And when the VGS is equal to 0, it will provide the constant current. So MOSFET is providing all the types of current here, constant current, increasing current as well as decreasing current. But if you take the junction field effect transistor, it will operate in only depletion mode, so that it can provide only constant current as well as decreasing current only. It cannot provide the increasing current. So that is the drawback of the junction field effect transistor. So in order to overcome that drawback only, we are moving for the MOSFET. So MOSFET is providing all types of drain currents here by varying the different voltages. So next characteristics are transfer characteristics between the VDS ID and VGS. So here if VGS is negative means the current is decreasing here, and if VGS is positive means the current is increasing. So in this case also this is the depletion region operation and this is the enhancement region of operation. So these are the transfer as well as drain characteristics of the N-channel depletion MOSFET. And next type of MOSFET is enhancement MOSFET. So in that I am considering the N-channel enhancement MOSFET. To construct N-channel enhancement MOSFET, again I am considering the P substrate, okay. On this P substrate I am diffusing two pieces of N type of materials, and upon this I am providing the metal layer in order to make the contacts of terminals. Those are source and drain terminals, and between these two again I am providing the silicon dioxide layer. So the impedance of this silicon dioxide layer is from 10 power 10 to 10 power 15 ohms. It is very high. And upon this we are providing again the metal layer. This indicates the gate terminal. So here if we observe, there is no physical channel between the source and drain terminals in the case of enhancement MOSFET. Again here also we can tie this substrate as well as source terminals, so we can make it as normal source terminal. So this is the construction of the enhancement MOSFET. There is no physical channel. So while coming to the operation of the enhancement MOSFET, so enhancement MOSFET will operate for only positive values of VGS only. It will provide the current for positive values of VGS. It will not provide the current for the negative values of VGS. So that's why it is called as enhancement MOSFET. So here between gate and source we need to provide the positive voltage, that is VGS, and again this one is common between drain and source. Always we need to provide the positive voltage. Okay. So in this case, because of this VDS, the current ID is flowing in the device. This one we discussed in the depletion MOSFET. But how the channel is forming here, we have to see. So here the positive terminal of the battery is connected to the gate here. Okay. In the P type of substrate, the electrons are the minority carriers. Because of this positive polarity, that electrons are attracted towards the gate terminal here. So if we increase more and more VGS voltage, more number of electrons are formed near the gate or between the source and drain terminals. So this formation of electrons only we can call it as channel in the case of enhancement MOSFET. So here channel is nothing but movement of electrons between the source and drain terminals here. So here in this case, if VGS we are providing means we will get the ID current, that is in the saturation region we will get that current. Okay, if you along with the VGS voltage, if you increase the VDS voltage, what will happen means the charge carriers, the electrons are moving towards this terminal also. So because of this movement of the charge carriers or electrons from drain to this positive terminal, the channel length will be reduces here. Previously the channel length is here, and when you increase the VDS voltage, now it will change to here. If you still increase the VDS voltage, the channel length may decrease here. So if the channel length is decreasing like this, means this we can call it as pinch off region. The channel length is reduces across the drain terminal, that we are indicating with the pinch off region. But in the saturation region of the operation, Even though channel length is reducing means current conduction in the device will increase. Why? Because the length and width of the channel is directly proportional to the resistance in the channel. So here length and width, both the parameters of the channel are reducing means definitely the resistance value will also decreases. So in the channel the resistance level is decreasing means automatically the current will increase. So that's why in the saturation region, the current ID will increase when you increase the VDS voltage. So that we'll see in the characteristics. So these are the drain characteristics of the enhancement MOSFET. So I have already mentioned it will operate for only positive values of VGS. It will provide the drain current for positive values of VGS. So when VGS is equal to low, very low value or equal to 0 means you will get the drain current is also 0. And if VGS is increasing means correspondingly the drain current will also increase here. So generally the MOSFET will operate in 3 regions, that is cutoff region, ohmic region and saturation region. So cutoff region means when you are not providing any voltages to your device, in that case we will not get any current. So this one we can call it as cutoff region. And where we are getting the constant or increasing current, that indicates the saturation level. And where if you increase the voltage, that corresponding increment in the current you are observing. So this particular region we can call it as ohmic region or triode region. We can also call it as triode region. So in this particular ohmic region or triode region, we can use MOSFET as voltage variable resistor. Why? Because how much voltage we are providing, that much corresponding proportionate current we are getting here. So that's why we can use it as voltage variable resistor in the case of ohmic region operation of the MOSFET. And next, while coming to the symbols of the MOSFET, here I am taking first N-channel MOSFETs. In that N-channel MOSFET, I am taking depletion mode as well as enhancement mode. So in the case of depletion mode MOSFET, we are using 3 terminals, gate, drain as well as source. So this line is solid line between the drain and source here. This solid line indicates the existence of physical channel between the drain and source. But in the case of enhancement MOSFET, there is a gap between the drain and source terminals. So this gap indicates there is no channel physically present between the drain and source terminals. And why we are combining these two means, here this one is substrate. So we tied both the substrate and source terminals and we made it as one terminal as source. So that's why these two terminals are tied together here in both the depletion as well as enhancement mode. So in the case of N-channel MOSFET, always the drain current direction is invert the device. That may be the depletion mode or in the enhancement mode. And similarly, if we take the symbols for the P-channel MOSFET, the total symbol is same, but the current direction is outward here in the case of depletion mode as well as enhancement mode. And while coming to the application of the MOSFET, we can use it as a switch. So in the cutoff region of operation of the MOSFET, we can use it as open switch. And in the saturation region of operation, we can use it as closed switch. So first I am taking the operation of the open switch here. For that I am taking one enhancement type of MOSFET here. It is enhancement N-channel MOSFET here. So to operate it as open switch, the input should be tied to ground here. The first condition is input should tie to ground. And then if we observe the output, what we are getting here, we If the input is making it as ground, means we are not at all providing any voltage for the device. That is nothing but we are providing the gate to source voltage is less than the threshold voltage. Threshold voltage means the voltage required for the device making to conduction state. So that required voltage we are not providing here. Okay, we are grounding the input as well as gate to source voltage also we are not providing required threshold voltage level. So that's why in that case MOSFET is in the off state or cutoff region. So once the MOSFET is in cutoff region means there is no drain current will be flowing here. So drain current is not flowing means we can say it as open switch. It is not providing any voltage as well as current means, so that we can say it acts like a open switch. But what is our output? How much supply voltage, that is VDD, we are providing, that we will get it as output here. So in this particular situation, we can call it as MOSFET acts like a open switch. The conditions are input should be grounded and we should maintain gate to source voltage should be less than the threshold voltage. And next one is we have to operate the MOSFET in the saturation mode to make it as closed switch. So in that case, the input should be tied to the drain voltage or supply voltage, and also we need to maintain the gate to source voltage should be greater than the threshold voltage. So if we maintain these two conditions, the MOSFET will operate in the saturation region and it will be on, so that the drain current will be flowing in the MOSFET. Okay. So once the current is flowing in this particular circuit, I am representing here it as closed switch with the on resistance. And what about output here? Output we will be getting here it as VDS voltage, that is 0.2 volts due to resistance, RDS resistance. So we can say MOSFET is operating in the low resistance region or in the saturation region, or it acts like a closed switch when you are providing the VGS is greater than VTH voltage, and if you are tying the input voltage to the supply voltage, that is VDD. So in this way we can able to operate MOSFET as open switch as well as closed switch. So along with this, MOSFETs are also used for constant current source as well as wherever we require the high input impedance applications. In that cases also we can utilize the MOSFET. So this is about different types of depletion mode MOSFETs as well as enhancement mode MOSFETs. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.